Hello dear student, welcome to another lecture in Dynamics of Rigid Bodies. This is lecture number 5 in this series. So far we have learned about moment of inertia, theorems of moment of inertia and some moment of inertia of some of the rigid bodies. In today's video, we will learn about kinetic energy. Kinetic energy of rotating bodies, kinetic energy of a rolling body, and also the moment of inertia and kinetic energy of certain rigid bodies. Now, what is kinetic energy? Kinetic energy is the energy possessed by a body by virtue of its motion. It is the energy possessed by a body because of its motion, the energy contained in a body because the body is moving. And this kinetic energy is proportional to its mass and also square of its velocity. Now, what is rotational kinetic energy? Rotational kinetic energy is the energy possessed by a body by virtue of its rotation. Again, rotational kinetic energy is also proportional to mass and also the square of rotational velocity or angular velocity omega. And we can see that the rotational kinetic energy can be found for a rigid body as follows. Consider a rigid body. And consider this body is rotating about an axis through a point O and its rotational velocity, that is angular velocity, is omega. Consider a mass m at a distance r1 from the center of rotation, the point through which the axis passes. Consider this mass m1 at a distance r1 from the point of contact, the point of oscillation. Consider the mass is moving with a small velocity vi. That is, if the body is rotating about this axis, if the body is rotating, it has a rotational kinetic energy omega, and consider if it is rotating with a rotational kinetic energy omega in this direction, then any point mass here will have a linear velocity in this direction. Let that be v1. Now, the rotational kinetic energy or the kinetic energy of this mass m1 can be calculated using the formula kinetic energy is equal to half into mv square. Here, since the mass is m1 and the velocity is v1, we can write kinetic energy is equal to half into m1 v1 square. But we also know that the linear velocity and the rotational velocity is related by the equation v1 is equal to r1 omega or v is equal to r omega. Here v1 is the velocity at a distance r1. We can write v1 is equal to r1 omega. So instead of v1, we can substitute r1 omega. Therefore, kinetic energy, here it becomes the rotational kinetic energy, will be equal to half into m1 into, instead of v1, we can write r1 square omega square. Thus, the kinetic energy of the mass m1 is equal to half m1 r1 square omega square. But the body is not just the mass m1. It has several other masses distributed all over the body. Therefore, the kinetic energy of the entire body will be equal to the sum of kinetic energies of all the masses. That is, we can write the kinetic energy of the entire body will be equal to kinetic energy of all the masses. That is, kinetic energy of the mass m1 was calculated to be m1 r1 square omega plus kinetic energy of the mass m2 will be same as that as m2. Here m2 is at a distance r2, therefore we can write m2 r2 square omega. Omega is constant for every body. Also for a mass m3 I can write m3 r3 square omega, and several other masses which is located all over the body. I know that the moment of inertia I for a mass m1 at a distance r1 is calculated as m1 r1 square, right? The moment of inertia of a mass m1 at a distance r1 is calculated as m1 r1 square. Therefore, can I substitute this m1 r1 square as I1 and this m2 r2 square as moment of inertia of the second body and m3 r3 square as moment of inertia of the third body. Therefore, this can be written as the kinetic energy can be written as the sum of half into the moment of inertia of all the bodies, that is m1 r1 square plus m2 r2 square plus m3 r3 square plus etc. The moment of inertia of all the bodies, the moment of inertia of all the bodies multiplied by omega. Here, moment of inertia of all the bodies about all the masses m1, m2, m3 about the point O is certainly the moment of inertia of the entire body about this point O. Therefore, instead of writing this term, I can write half into the moment of inertia of the entire body about the point O through this axis into omega. Therefore, kinetic energy, the rotational kinetic energy of a rigid body is written as half I omega square. Sorry, I've missed a square over here. All these points has a square. Half I omega square. In linear motion, we have half m v square. Therefore, its rotational analogy is by changing mass into moment of inertia and linear velocity into the rotational velocity or angular velocity omega. I have discussed this relation with mass and moment of inertia in our first video. The mass is a measure, the inertia, the linear inertia is a measure of mass, and the rotational inertia is a measure of moment of inertia, as we have already discussed in our first video. Therefore, moment of inertia is the rotational analogy of the mass, and the rotational velocity omega is a rotational analogy of the linear velocity v. Thus, by resubstituting or reconnecting with the linear kinetic energy, we can write the rotational kinetic energy as half into I omega square. Therefore, a body which is rotating about an axis with a rotational velocity omega will have a kinetic energy half I omega square, where I is the moment of inertia of that body. Now, what will be the kinetic energy of a rolling body? A rolling motion is a combination of a rotation as well as translation. Now consider this particular ball. This ball is having a linear velocity in this direction v, and also it is rotating. It is rotating with an angular velocity omega. That is, you can see the center of mass of this body traces a straight line in this direction v. The center of mass of the body here traces a straight line direction and it moves with a velocity v. Therefore, we can consider it as a body which is moving or which is translating in a straight line direction. Also, the body, the upper part of the body, when it moves in the first direction, when the upper part of the body moves in a velocity v, then the lower part of the body is moving with a velocity minus v. Therefore, this has a couple and it rotates. It rotates with an angular velocity omega, and this angular velocity and v is related, and it is related by the equation v is equal to r omega, where r is the radius. Therefore, kinetic energy of a rolling body can be the kinetic energy of its rotation plus kinetic energy of its translation. Let's find how it will be. Consider this body and consider an axis which is coming out of the plane through the end part of the ball. That is, ball is placed in a plane and it is rotating about an axis which is coming out of the plane tangential to the ball. And we are going to find the kinetic energy about this axis, because when the ball is rolling, it touches the plane. When the ball is rolling in this direction, when the ball is rolling with a translational velocity v, then this is the point at which we can consider all the particles are going in around. That is, this is the axis of rotation. This arrow which is marked in white is the axis of rotation of this ball at a point P. Therefore, we are going to find the kinetic energy at the point P about this axis. And since we have already calculated that the kinetic energy is equal to half I omega square, here I, moment of inertia, is calculated about this axis at a point P. Therefore, kinetic energy at the point P is equal to half IP omega square. Now, consider this ball and the moment of inertia of this ball about its center of mass is already known. The moment of inertia of any rigid body about its center of mass is known. Now, this axis which we have drawn here is actually a tangential axis. This is the tangential axis P. And this is the center of mass axis passing through its center of mass. Therefore, using parallel axis theorem, we can write that the moment of inertia about P, that is IP, moment of inertia about P is equal to moment of inertia about the center of mass plus mass of the body into distance between these axes. The distance between these axes is nothing but the radius of the ball, that is m r square. Therefore, the kinetic energy about the point P can be calculated as half IP omega square is equal to, we can substitute for IP as ICM plus MR square into omega square. Therefore, on substituting, I can write this as, what I have here is the kinetic energy. This term is entirely the kinetic energy of that body, of a rolling body. Therefore, kinetic energy of a rolling body is equal to half ICM omega square. Now, what will be this? This is the kinetic energy of the body when it was rotated about its center of mass. Since the body is rolling, the body is not rolling about an axis which is passing through the center of mass. The body is always rolling towards about a tangential axis. That's why we have to find the moment of inertia about a tangential axis which is coming out of the plane. Now, this term can be written as, I can write kinetic energy is equal to half ICM, that is moment of inertia of the center of mass, into omega square plus half mr square omega square. Again, I know that the linear velocity v is written as r omega. In this case, r is the radius of this ball. Therefore, I can write r omega as v. Therefore, r square omega square can be written as v square. Therefore, the kinetic energy of a rolling body is equal to half I center of mass into omega square plus half mv square. We already know that the moment of inertia of a rolling body, moment of inertia, this is the moment of inertia of a rotating body. This is what we have already found. This is the moment of inertia. This is the kinetic energy of a rotating body. And this is the kinetic energy of a body which is moving in a straight line, that is translational. Since rolling is a combination of rotation and translation, the kinetic energy of a rolling body is also equal to the rotational kinetic energy plus the translational kinetic energy. Now again, let's do some mathematics and find how to resubstitute all these. What we have is kinetic energy is equal to, kinetic energy of a rolling body is equal to its rotational kinetic energy, that is half I omega square, plus its linear kinetic energy, that is half mv square. We can write ICM, that is moment of inertia about the center of mass, as mk square, where k is the radius of gyration. Hope you remember radius of gyration. We have learned it in our first video. Radius of gyration is the radius, is the distance from an axis to a body, to a point in the body where the mass is assumed to be concentrated. That is, consider an axis here and we have a rigid body here, and let this is the center of mass. Then this distance is the radius of gyration k. We have defined it in our first video. Therefore, we can write the center of mass, moment of inertia of the center of mass is equal to mk square, where k is the radius of gyration. Therefore, we can rewrite this equation as half mk square omega square plus half mv square. Now, we know that the omega square is equal to, what is omega square? We know that V is equal to R omega. Therefore, omega will be equal to V by R. Therefore, omega square will be equal to V square by R square. Therefore, instead of omega square, I am going to substitute V square by R square. Mk into V square by R square, mk square into V square by R square plus half m V square. Let me take half mv square as common from this. Half mv square, when taken as common, I will get k square by r square from the first term, and the second term turns out to be 1. And this can be the kinetic energy of a rolling body. Therefore, I can also write the kinetic energy of a rolling body in terms of radius of gyration and the radius of the body as half mv square into k square by r square plus 1. This is the kinetic energy of a rolling body. What does this equation tells us? This equation tells us that whichever body which has k square by r square to have a higher value will have a higher kinetic energy. Let's see the difference. We know that the kinetic energy is equal to half mv square into k square by r square plus 1. That is, as k square by r square increases, as this term k square by r square increases, the moment of inertia also increases. Consider different types of body with same mass, with same linear velocity, but different k square by r square. Then the kinetic energies will be different. And this k square by r square owes completely to the geometry of the body. That is, it owes completely to how the mass is distributed and what is the shape of the body. You can see that the k square by r square of a hollow cylinder or a ring is equal to 1, while the k square by r square value of a solid cylinder or a disc is half, and that of a solid sphere is 2 by 5, and that of a hollow sphere is 2 by 3. That is, when all these things, when a disc, a ring, and a solid sphere and the hollow sphere, which has the same mass and same linear velocity, is rolled, then the particle with the highest k square by r square value, that is definitely the cylinder or a ring, will have a higher kinetic energy, will tend to have a higher kinetic energy. How can we find the k square by r square value of a hollow cylinder? Let's do some of these. Some examples. We know that the moment of inertia ICM of a ring, moment of inertia of a ring is calculated. We have already calculated it as mr square, and this moment of inertia is calculated about its center of mass. But we know that the moment of inertia about the center of mass is nothing but mk square. Therefore, we can write mk square is equal to mr square in terms for a ring. Therefore, we can just cut it out and write k square by r square value of a ring. K square by r square value of a ring is equal to 1. This is same as for a ring and also for a hollow cylinder. Therefore, k square by r square value of a ring and a hollow cylinder is equal to 1. Similarly, we know that the moment of inertia of a disk about its center of mass. We have already calculated it. We have calculated it as mr square by 2. Therefore, we can write mk square is equal to mr square by 2. Therefore, k square by r square of a disk or a solid cylinder is equal to 1 by 2. You can see the symmetry. A hollow cylinder can be considered as made up of a number of rings, right? When we cut a hollow cylinder, the cross section gives us a ring. A hollow cylinder, a cross section will give us a ring. But in case of a solid cylinder, the cross section will nothing but be a disk. Therefore, the k square by r square value of a disk or a solid cylinder is equal to 1 by half. Similarly, for a solid sphere, we have calculated the moment of inertia of a solid sphere as 2 by 5 mr square. Therefore, mk square will be equal to 2 by 5 mr square. Therefore, k square by r square value of a solid sphere is 2 by 5. Similarly, for that of a hollow sphere is 2 by 3. Now, 1 is a greater value among these. And next comes half. Next comes 2 by 3. And next comes 2 by 5. Half is nothing but 0.5, but 2 by 3 is again equal to 0.666. It's a recurring decimal. Therefore, half is greater, 2 by 3 is greater than half. Therefore, we can consider that, we can see that when these bodies, that is when a hollow cylinder, a solid cylinder, a solid sphere and a hollow sphere which having same mass and same linear velocity is rolled, then this hollow cylinder will have a greater kinetic energy. Then the hollow sphere will have the next greater kinetic energy, followed by a solid cylinder and then by a solid sphere. Therefore, when rotated down an inclined plane, a solid sphere will reach the least area, that is reach the slope at the highest speed. Then a disk will reach, followed by a hollow sphere and followed by a ring. That is, when we rotate all these things, a ring, a hollow sphere, a disk and a solid sphere. Instead of ring, when we can also rotate a hollow cylinder because both of them has the same moment of inertia about its center of mass. Therefore, again instead of disk, we can rotate a solid cylinder. Therefore, when we rotate a ring or a hollow cylinder, a solid sphere, a disk or a solid cylinder and a solid sphere about an inclined plane, a solid sphere will reach the least point, reach the ground first, followed by the disk or the solid cylinder, then followed by the hollow sphere and then followed by a ring, provided all these bodies has the same mass m. Therefore, we can conclude that in the first video, the rod contractor C. Pavitran was not able to control, and his friends were not able to control the rod roller. It was not the mistake of the driver Sulaiman, it was just the way in which the road roller is made. The wheels of the road roller are made to be solid cylinders, made in the shape of solid cylinders, which offer them a good kinetic energy, that is, it reaches the ground when rotated about an inclined plane. It reaches the ground with a greater speed, that is, it reaches the ground first, and the controlling its a moment of inertia, the controlling its motion is difficult because it has a higher moment of inertia. Higher moment of inertia means higher will be the resistance offered by that body to any change in motion. Maybe to stop or to start a motion, higher will be its resistance offered by that body to stop or start. Therefore, the road roller in effect is very hard to control because of the mass of the wheels and the shape in which they are designed to be. So dear student, so far we have learnt about moment of inertia, theorems of moment of inertia, and also we have seen different moment of inertia of different rigid bodies. And today we have learnt about kinetic energy of a rotating body, a rolling body, and also found how these rigid bodies behave under rolling. And this lecture series will end in one more lecture that will be in flywheel. See you next week. Thank you.